My name is Nick Janis, and I'm a senior technical fellow at CAE, and I work for the technology and incubation team. So I pretty much get to do everything that nobody knows who to give it to, which usually is some pretty interesting stuff, so I tend to have quite a bit of fun. And some of the stuff I'm going to talk about here came from that. So I can't see everybody in the audience, but there's some familiar faces. I'm sure some of them are not super familiar with CAE, so I'm always kind of surprised when people aren't familiar with CAE, but I guess if you're not in our industry, then you probably wouldn't be. So I'm going to subject all of you, unfortunately, to our corporate video, which I think is actually pretty good, so we'll just go quickly through that. All right, so as you saw in the video, we operate in kind of 3 different business lines, but fundamentally our objective is to train people for the critical roles they fill, and we use digital immersion as the technology to do most of that. So high-tech training and operational support based on digital technologies, and our vision very much being a partner of choice in civil aviation, defense, and healthcare. We also have a deep drive towards corporate and social responsibility, both internally and externally. 3 lines of business, as we said: civil aviation, where we deliver over 1 million training hours annually to pilots, cabin crew, and maintenance personnel. I like to say that if you took an airplane here, almost certainly your pilots were trained on CAE equipment, and more than likely they were trained either by CAE personnel or directly or indirectly. Defense and security, we operate worldwide supporting allied nations, again using digital technology for training and operational support. And we introduced a lot of new technologies using immersive capabilities in the healthcare market to improve patient outcomes. We're a global business with over $3 billion in revenue in the last fiscal year. We're based in Canada, but we primarily operate globally in 200+ locations with 13,000 employees. Our number 1 group in CAE is pilots, and after that is engineering technical folks. So we have a large group of technical people developing solutions for our different markets. Our revenue is split mostly between civil aviation and defense, and with a growing part in healthcare. And we have a mix between products and services, and half of our mix geographically is in the US, with Europe, UK, and the rest of the world. US is the world's largest defense spender, so it's not a surprising outcome. So last year here at Unreal Fest, we talked about the evolution of our visual solution. And going back to the early 90s, where we essentially rolled our own solution from hardware to software. So we literally built large circuit cards with FPGAs programmed at very low levels to get the kind of mind-boggling performance of 6,000 polygons. In the 2000s, we started adopting commercial solutions, specifically commercial graphics cards that were growing in capability. We still built our own cards. We ganged together multiple graphics chips to achieve the performance we needed. A lot of it was driven by things like anti-aliasing. But the software was all our own based on an OpenGL stack. Today, as we announced last year, our new visual solution, CAE Prodigy, is based on completely commercial platforms, both hardware and software, and the basis for the software stack today is the Unreal 5 engine. As Seb mentioned, I was in Singapore last week for the OGC member meeting, and I was lucky enough to attend some great presentations. And one of the, or a couple of the big topics we had at OGC was the metaverse, digital twins, and the overlap, and some interesting discussions about what they represented. There was one excellent presentation from the Singapore government, Singapore Land Authority. They had built this very interesting application that they called the metaverse application, but then they kept referring to it as a digital twin, because in fact it was both. It was a highly immersive representation of the city of Singapore, being fed by sensors, video cameras, data from GIS applications all over, brought into the same universe essentially. It's on YouTube, so if you're interested, I can send you the link. But it's a fascinating application of the two together, and also tends to highlight, I think, the challenge of integrating many different systems together, and of course, the interoperability associated with them. So what if we wanted to represent an entire country? Like, what would we need to put together? So we could start with the population, so modeling the citizens of the country. We would model the urban centers as hubs of activity and all the complexity associated with them. We'd show where all the critical infrastructure would be, and we could also create use cases around defense and security. And of course, many, many other aspects could be brought together. But of course, the more you bring together, the more complicated the solution becomes. And bringing together these complex architectures really requires flexible, scalable, and interoperable solutions, which means you start to come up with diagrams like this, and this is a fairly simple one based on one of the use cases that we did, but of course it could get much more complicated. So how do you select and assemble the pieces in your solution when you try and put together something like this? So you can break the kind of the interconnection problem in 3 dimensions. So the 3 are integratability, interoperability, and composability. And I said all 3 without making a mistake, incredibly. So the first one, integratability, typically related or associated with infrastructure, hardware, computers, networks, storage devices, but also sometimes low-level software that provides some of the capability as well. On the interoperability front, it's primarily associated with software and the interfaces they provide, the APIs, or whatever other capability they have for connecting to other software or to the outside world. And finally, composability, which is typically associated with the models. How do the models work together? How do they interact? What are the expectations between them? And this is an area that can be a significant challenge. So interoperability is a continuum, and for those of you who are familiar with the levels of conceptual interoperability model, sorry, my brain stopped there for a second, then this will all look very familiar. So the model isn't old, but it's always worth referring to it because of the things that we know intuitively anyway, but we see this spelled out very specifically. So at the lowest level, you end up with no interoperability, so these are just separate standalone systems where data isn't shared. At the next level, you're really achieving technical interoperability, so the ability to communicate, so networks and communication protocols are identified, but you're sharing data, but you have no understanding of how to unpack that data or how to use it. At the next level, you achieve this syntactic interoperability, where now you use a common protocol for that data, so you can grab it, you can unpack it, you know exactly how to read it. But then at the next level, you're achieving what's called semantic interoperability. And here you're actually starting to understand what the data represents. So in the simulation world, this usually means something like a Federation Object Model or a FOM that's part of HLA. At the next level, you're achieving pragmatic interoperability. So you're starting to understand not only the data and what it means, but also some of the services associated with it, so how you can act on the data. Then at the next level of dynamic interoperability, you're also understanding what impact those services have and what the performance might be from one system to another. So you can't just expect things to act the way you want them to. All models have limitations, and some of them are dynamic in nature. And finally, at the highest level, you're achieving conceptual interoperability, where you not only can do everything we just talked about, but the different worldviews of each model are kind of known to each other. So some of the aspects or limitations that aren't clearly spelled out are available because you're sharing a lot of the same concepts. So there's no silver bullets, and I can't really say it better than this RAND study from many years ago that basically said this idea of plug and play is fatally flawed for complex models. They basically say software composition on its own is difficult enough, but when you're trying to actually compose models, it's even harder because models are fundamentally different. In the simulation world, there's a process called the DCEP that helps take you through this integration of different models. It's meant for distributed simulations, but there's one step in the process called the perform conceptual analysis. And really, it's just a reminder that there are certain steps you need to take if you want to avoid problems downstream. So it's fairly straightforward stuff, but it's things like, what's the objective? What are the scenarios? What are the different models you need to bring together, and how do you expect them to interact? And the easier you do this in the design cycle, the better chance you have of succeeding later on. Again, none of this is rocket science, but sometimes we forget to do it, or we're often short on time, and we tend to skip some of these steps and pay the price later on. The good news is standards help. So standards help like crazy. And if we just look at Unreal, for example, in the area of kind of networking interoperability, there's support from plugins for DDS, from the object management group, for SIGI from CISO, and of course from HLA from the IEEE. On the geospatial data front, there's a raft of OGC standards that help us, especially on the 3D side with I3S, CDB, and 3D tiles. There also exists some on the instructional data side with XAPI for capturing instructional information, and also SCORM for lesson management systems. So yeah, in fact, standards help a lot, and where you can leverage them and still achieve your objectives, then you wholeheartedly should. Okay, let's talk a little bit about one of the use cases that we came up with, and it was really the diagram I showed before where we assembled different systems together. So we wanted to create a use case around kind of a civil security issue in London caused by a cyber attack on the power grid. So we started with the population of London at scale, with all 12 million people mapped out to the city, and we used census data to lay them out in a more or less correct fashion. You can't get individual locations of people, so we just use the variety of geospatial data to lay them out. And for the most part, I think they make sense, at least for the purposes of our use case. Then we needed a digital twin of London, so a 3D representation of the city, and we found a partner who had done high-resolution aerial mapping of London, and provided us this data, which we transformed into 3D tiles, and then streamed into a web browser, which is what you're seeing here using Cesium. So again, leveraging the OGC 3D tile standard and the Cesium plugin, in this case for web, but we're going to use it for Unreal also, really got us going quickly. So as I mentioned, the cyber attack was on the power grid. So again, we looked at the data, open data for the actual distribution network in London, and there's only so much information you can get, but we essentially recreated it to the best of our ability. and had the ability to disable different power stations and see the effect they had on different areas of London. So that was another simulation in our system. We also wanted to look at how the population would react. So we created an AI-based social media model. So interestingly, we used AI to synthesize the creation of social media posts, and then we used another AI model to analyze those to get the sentiment of the population, to see over time, as the cyber attack unfolded, what was the sentiment of the population. And also, I think probably just for fun, our AI people created a deep fake of the London mayor getting on TV and telling everybody not to worry, which of course had the exact opposite effect. We also created a pattern of life simulation using an agent-based crowd model. And normally the pattern of life has people going from home and work during the course of the day. But because of the cyber attack and the power failure, we changed their behavior and said, oh, they're going to be not happy that the government didn't protect them from a cyber attack. And so they're going to gather and protest in Trafalgar Square. And while this may not be super realistic, it was kind of interesting from a modeling perspective. So as the crowd starts forming in Trafalgar Square here, you can see the people walking briskly, sped up, and you can see the crowd starting to grow. And again, we used here the same 3D tiles geospatial data that we saw before, but rendered directly in Unreal. So that was a benefit. We used it exactly as it was. We did upgrade a few of the 3D models here. So Nelson's column is a new model that we created to get more resolution, as well as some of the light standards in the subway entrances as well. And because it could be a security risk, we had emergency vehicles show up to block the streets so that people wouldn't get run over by cars. And that simulation was done directly in Unreal. And then finally, this is what it starts to look like when the crowd gathers in Trafalgar Square. They're all very well behaved. They're not jumping in the fountains. But it's worth explaining that because there's a separate crowd simulation running in this case, each individual that you're seeing here is a fully simulated person that does pathfinding, collision avoidance, all of that. Even the ones way in the back, you can't even see if they're moving. They are, in fact, fully simulated. So we couldn't do that in Unreal. We're using Unreal 4 at the time. So we did that in a separate crowd simulation and had to ship the data over to the rest of the systems. So recap that use case. So 3D tiles support for Cesium and Unreal and the web client was critical for our geospatial interoperability and really helped us out a ton in terms of dealing with geospatial data. Interestingly, as we had the pedestrians walking along the sidewalks, they would jump on top of trees and on top of canopies of storefronts, and that's because that's where the elevation was as far as the photogrammetry was concerned. So we had to create a separate digital elevation model, and we tried getting an available one, but it wasn't perfectly aligned with the photogrammetry, so we had to process the data to remove all the vertical features and create our own. And in the end, we made sure that people were clamped to the ground and not floating or underground. We had a challenge with Unreal when we tried to put in 100,000 independent agents, not just in terms of simulating them, but even when we did it externally in our crowd model, sending it to Unreal, we needed a different network stack. We looked at using DDS and HLA, but we had issues with it. So in the end, we just used our own custom network stack. And to render all those characters, we did it ourselves. But what we're seeing, especially with the new UE5 masks, there's a lot of capability there that nowadays we could have leveraged. And that's really one of the advantages of using commercial software is the continuous investment and improvement. So our next use case involved doing another whole country, in this case, Estonia. So we modeled all of Estonia based on their land board data, including a high-resolution model of the capital Tallinn, especially the Old Town, where the government itself had built a high level of detail models of the Old Town. And I visited Estonia, and it's kind of creepy how much it looks like the exact model there. Interesting in this use case, we added the defense side of things. So near the eastern border with Russia, we created a scenario around a paramilitary force that's actually invading the port and then moving to take over an industrial area near the port. So here you can see some of those vehicles that are being offloaded from the ship that had docked. And in this case, all the vehicles, the military vehicles and the ship, were modeled in a different system, a computer-generated forces application. So that had its own worldview with its own capabilities, its own limitations that needed to be integrated with the rest of the geospatial data, and then, as you'll see in a second, with the other systems associated with it. So here you can see all the military vehicles moving to the industrial area near the port. So here's another view, and of course they needed to interact with the people. So as part of our scenario, as this quasi-invasion was happening, then the local population initially moved to see what was going on, and eventually would start massing, which created challenges with the interaction between the pedestrians and the military vehicles. Remember, they were in completely different systems with completely different modeling expectations. So here the vehicles are coming down the road, as are the people, and in a minute you'll see there's a crowd of people already formed. There it is on the top right, which are massing near the gates of the port itself. So going over that particular use case, so it sounds like a fairly simple use case in terms of there's a scenario when military vehicles show up and people get concerned and they mass. But because we added a completely new system and a whole bunch of new interactions, it became exponentially more difficult. We also had a challenge with the geospatial data, which we didn't before, because these three systems, the crowd modeling, Unreal, and the CGF use completely different sets of data. And then finally, there was this interaction between the people and the vehicles at scale, which created a challenge for us. Some of the specific challenges we had, I mean, it sounds kind of silly, but we had time synchronization issues between Unreal and the computer-generated forces application. We resolved it eventually, but it really shows you that you can't really take things for granted when you start assembling systems. This geospatial data alignment across the three systems was a challenge as well. So we had to make sure that the roads in one system were visibly the roads in another system, and the pedestrians were on the same roads or pathways in another one. So this is a real challenge, and anyone who's worked with geospatial data knows that you can't take any of it for granted. The other interaction thing was the crowd simulation models every agent, so every person is a circle. So it kind of makes sense for when you're modeling humans. But the problem is, how do you model vehicles? Because the crowd model needed to know where the vehicles were to avoid them, or for the vehicles to avoid them. But the vehicles, of course, are not shaped like circles. So this was actually a limitation in the system that we discovered kind of later on, and would actually have to be enhanced in one way or another. Because the CGF itself can handle any arbitrary shape, but the crowd modeling only handles one shape. The other issue we had was the CGF can scale to a few thousand entities. It was very high fidelity, and it was really intended for kind of that scale of scenario. So we had to figure out how we would interact with potentially tens of thousands of people. So a crowd of people blocking a tank, for example, we can't send tens of thousands of entities to the CGF because it would completely bog down. And to date, this is not something we've fixed. We have some ideas about how to fix this, but like creating blobs of people, for example. But this is really more indicative of the fact that there's this almost impedance mismatch between one simulation and another simulation. One can do very large scale, very high performance, but limited modeling, and the other one is the opposite, essentially, very high fidelity, smaller scale, and virtually limitless modeling. And bringing the two together is really one of the challenges of interoperability and of essentially the composability aspect of different models. So even though the two could communicate, and we made them communicate, we didn't know how to resolve some of the modeling differences between them. So in summary, every combination of models and data results in unique interoperability challenges. This is why you do system engineering, and that's why putting together a system of systems is an engineering challenge. The good news is that standards can help, like I said. So especially the pre-integrated support for standards helps a lot in terms of the interoperability. I talk a lot about the challenges we faced, but the fact is that a lot of things we did just came because of the capability that was built in, either through plugins or through the systems themselves, which was a tremendous benefit. Composability, as I mentioned earlier, at the modeling level, is a challenge, and I think always will be, right? Because there are these tacit assumptions in the different models that are put together that sometimes you only discover afterwards. And I remember I was listening to one presentation at a conference, and somebody was saying, wouldn't it be great if there was this language you could use that would perfectly describe every aspect of a model, and there was no ambiguity associated with it? And then he said, oh, that's called code. But anyway, the challenge is there, so the openness of the solutions really helps in terms of resolving issues, especially ones buried deep inside some of the modeling constraints. And that's it for me. Thank you very much.